Electrostatics, electric boundary conditions, problems, series on electromagnetic field theory, lecture number 1.71. There are two statements considered as electric field boundary conditions. One says that tangential component of electric field is continuous. Another statement says normal component of displacement density is continuous except in the presence of surface charge density. These two statements, they are called electric boundary conditions. These are highly useful in estimating electric field intensity when field conditions on the other side of the boundary or interface are known. In the present session, we consider two problems. In the first problem, we consider a charge-free interface, and in the second problem, we consider an interface boundary carrying certain surface charge density. In both the cases, we try to estimate fields on one side of the interface from the fields on the other side of the interface. Before moving further, let us recollect electric boundary conditions. 1. The tangential electric field intensity is continuous across the interface, irrespective of the conditions that are there over the interface. The normal component of D, displacement density, is discontinuous across the boundary by an amount equal to surface charge density sigma. If surface charge is not there over the boundary, then normal D is also continuous. Now we consider a problem involving charge-free interface. The electric field intensity in medium 1, the free space, is given by E1 equal to 3x cap plus 2y cap plus 4z cap volts per meter. Find D2, E2 in medium 2, whose dielectric constant is 3. The interface is x equal to constant, and then we have to consider y equal to constant also, and also angles made by E1 and E2 with the interfaces. Okay, solution. E1 is available. Find D1. D1 equal to epsilon 1 E1. Multiply. Epsilon 1 is epsilon naught, because it is free space. Medium 1 is free space. Now, before moving further, the thing is, we have to identify the normal components and tangential components in the expression of D1 and E1. This identification is possible only if we know the nature of interface. It is given that x equal to constant is the interface. X equal to constant is equation of a plane. It is a plane parallel to YZ plane. Therefore, one can easily identify that YZ components are tangential components, whereas X component of the field is normal. So this is normal, whereas these two are tangential. This is normal, these two are tangential. With this understanding, let us move. D1 is available. Now dN1. dN1 is X component of D1. This part is X component. Tangential components are Y and Z components. Okay. After identifying normal and tangential components, let us move further. D2 is, it is written here as dN1 plus epsilon 2 by epsilon 1 dt1. D2 is expressed in terms of D1. Actually, it is an expression D2 in terms of dN1, dt1. It means in terms of D1. How this expression has come into being? It is quite simple. D2 can be D2. It can be decomposed into two parts, dN2 plus dt2. But normal components are continuous. D, normal component, is continuous. Therefore, you can simply write it, replace dN2 by dN1. Finish. When it comes to dt2, it can be written as epsilon 2 et2. But et2 is equal to et1. But et1 equal to dt1 by epsilon 1. So epsilon 2 by epsilon 1 dt1. So this is the way d2 is expressed as in terms of dn1 and dt1. dn1, dt1 are available. Substitute, we will be getting this expression. Once d2 is available, e2 is d2 by epsilon 2. Using that, one can get this. Now, angles. We are asked to find out angles made by E1 and E2 with the interface. See, this is the interface. Angle made by E1 and E2. First, we consider E1. Angle made by E1 with this is interface. This angle you are asked to find out. In this case, in the case of interface at x equal to a constant, this is x direction. Now theta 1 is required to be found. Then what we do is we consider E1 dot x cap. You consider this product E1 dot x cap. By definition, it is equal to magnitudes of E1 into magnitude of x cap into cos of the angle between the two vectors, this and this. The angle between them is 90 minus theta 1. Cos 90 minus theta 1 is sin theta 1. Therefore, sin theta 1 is E1 dot x cap by magnitudes of E1 x cap. Theta 1 becomes sine inverse of that fraction. E1 dot x cap, not E1 dot x cap. This is E1 dot x cap means you will be getting 3. E1 magnitude square root of 3 square plus 2 square plus 4 square gives you 5.38. X cap magnitude is 1, it is unit vector. So sine inverse gives 0.59 radian. Similarly, theta 2 also can be computed. Same process. Next we consider the second part, y equal to constant. Here the solution is processes. It runs on similar lines. This is y equal to constant interface. Therefore, y component is normal component and xz are tangential components. So dn1, we have already calculated d1 from E1. E1 into epsilon 1 is d1. In that expression, y component now is normal component, xz components are tangential components. d2 is dn1 plus epsilon 2 by epsilon 1 dt1. How this expression has come, I have shown already just now. So no need to spare any time for this expression. So substituting dn1 dt1 already available, dn1 dt1, we will be getting d2 divided by epsilon 2, you will be getting e2. Now angles can be computed same way, but you have to consider here E1 dot y cap. Then we will be getting angles like this. We consider another example. Here the interface carries certain surface charge density. Interface is located at z equal to 0. Region 1 is z less than 0. Region 2 is z more than 0. Okay. Now, what we are required to find out is d2, dt2, dn2. d1 is given. Displacement density in region 1 is given. You are asked to find out d2. Once d2 is available, with no time you can find out what is tangential component, what is normal component. How to proceed? Here what he did is, first from d1 he computed E1. E1 is d1 by epsilon 1. So E1 is available. Since across the interface tan E is continuous. Tan E is continuous. So dt2 is dt1, dt2 is dt2 is epsilon 2 ET2. But ET2 is equal to ET1. Tangential electric field is continuous. So he used this that relation here. ET1 is available. What are tangential components of E1? Z equal to 0 is the interface. Therefore, XY are tangential components. Z is normal component. XY. These two are tangential. So he substituted. Ultimately, we got DT2. Now, let us move further. Across the interface, normal D is discontinuous by surface charge density. Therefore, dn2 is dn1 plus sigma z cap. dn1 is 3. Magnitude only we have to consider. Sigma is given as 2. So 3 plus 2 z cap equal to 5 z cap picocoulombs per meter square. In this case, the field due to surface charge is aiding to field in region 2. Where is here? Region 2 is here. Now this is surface charge. What is the direction of the field due to this charge? Above the sheet, it is upwards. Below the sheet, it is downwards. Now you concentrate on region 2. In region 2, what is telling is the field due to surface charge is aiding in favor of field in region 2. Field in region 2 is upwards. In region 1 also it is upwards. It is upwards and this field is also upwards. They are in the same direction. Therefore, plus sign you have to use here. So dn2 is 5 z cap. Now d2 is dt2 dn2. dt2 is available. dn2 we have calculated just right now. Add these two, we will be getting d2. Now B aspect or B part also we consider. Now region 1 is z more than 0, region 2 is z less than 0. Across the interface, normal D is discontinuous by surface charge density. Therefore, dN2 is, of course, dN1 minus. Here we have used negative sign. Here plus sign, here minus sign. What is the reason? Reason is this. Now, in the present case, where is region 2? This is region 2. What is the direction of the field due to surface charge? It is downwards. But what is the direction of dN2? dN2 is upwards. dN2 is upwards. dN1 also upwards. But what is direction wise? What is the relation? It is downwards, opposing. It is opposing. That's why minus. 3 minus 2 z cap. In this case, note that field due to surface charge is opposing to field in region 2 and hence negative sign. So density d2 becomes d2 is dt2 plus dn2 is given by, see, already d22 we have calculated, dt1 now we have, dn2 we have just now computed. Adding this two, we will be getting d2. This is what I want to share with you regarding application of boundary conditions, electric field boundary conditions in obtaining fields on one side when the fields on the other side are available.